The Chengdu J-20 banked hard to the left. The pilot stared at his radar in disbelief. A missile had locked on and was closing fast. That was impossible. His jet was outfitted with cutting-edge stealth tech, and yet the missile was still screaming straight for him. He pulled hard on the controls, searching for space to escape. It was too late. The AIM-120 struck, turning the J-20 into a fireball. China's premier stealth fighter had been detected, targeted, and destroyed. And this is exactly the kind of threat Chinese and Russian stealth aircraft could face in a future conflict with the United States. In today's episode of the Infographics Show, we'll reveal the unexpected methods the US uses to hunt and destroy enemy stealth aircraft. But first, picture this. Chinese military intelligence picks up unusual activity at Camp Humphreys, America's largest overseas base, deep in South Korea. Satellite imagery offers few answers, only shadows and movement. Concerned Chinese commanders dispatch a J-20 stealth fighter to get a closer look. The J-20 lifts off from Shenyang Bailing Air Base, just 120 miles from the Korean border. 8 minutes later, it slices into South Korean airspace. There's no time to reach a cruising speed of around Mach 2 before the pilot is already soaring above Camp Humphreys. Still flying at over Mach 1, he should be able to sweep over the base, gather the intel, and vanish before anyone on the ground even hears the sonic boom trailing behind him. In theory, it should be a perfect stealth run. So imagine his shock when his headset crackles to life, an air traffic controller from Camp Humphreys ordering him to turn back immediately or face the consequences. The base's radars picked up his supposedly invisible jet, and worse, the data it's provided has already guided an F-18 Super Hornet into position, locked, loaded, and ready to fire precision-guided missiles. The entire process has taken just a couple of minutes. But how does the US do it so quickly? Well, the truth is that the detection part isn't actually that difficult to pull off, and depending on the circumstances, an enemy stealth plane can be detected from a considerable distance. And that's because current stealth technology doesn't actually give stealth planes a cloak of invisibility. Rather, it delays and complicates an enemy's ability to detect, track, and launch air defense systems against the plane. And you don't necessarily even need advanced technology to do the detection. Even standard commercial radar can detect smaller stealth aircraft. However, it's a much more challenging task to convert the signals detected into actionable intelligence for precision strike against the plane. Nevertheless, being detectable is a major chink in the armor of stealth fighters and bombers, particularly for China and Russia, over whom the US has a huge advantage in terms of stealth technology. So what are the vulnerabilities of Chinese and Russian stealth aircraft, and how does the US use these to detect them and then turn them into very expensive scrap metal? To understand that, we need to dig a bit deeper into what stealth technology is, what it does, and how it works. Stealth technology, also known as low observable or LO technology, is a collection of techniques designed to make military assets less detectable. And it's not just for aircraft. These methods are also used to reduce the visibility of ships, submarines, missiles, satellites, and ground vehicles. Think of it as camouflage for segments of the electromagnetic spectrum, or multispectral camouflage. Broadly speaking, when it comes to aircraft, the main aims of stealth technology are, in order of importance, the top priority is radar stealth, or the reduction of detection by radar. Then there's infrared stealth, or the reduction of infrared and heat detection. Next, acoustic stealth, or the reduction of the plane's acoustic signature. The last element is visual stealth. Let's take a look at each of them, saving the most important for last. Visual stealth aims to make the plane as invisible as possible to the naked eye, cameras, and other recognition systems. This is desirable for pretty much all military aircraft, not just stealth aircraft, and is achieved primarily through a simple method of paint. The idea is simply color the plane so it blends into the background. For instance, reconnaissance planes designed to operate at very high altitudes are painted black, the same color as the sky at that altitude. Conventional daytime fighter aircraft are usually painted a shade of blue, known as air superiority blue-gray, to blend in with the sky. Stealth aircraft are flown at night for maximum visual stealth, and so are painted black or dark gray. But even at night, the glint, the bright reflections from the cockpit glass or other smooth surfaces, must be minimized to maximize visual stealth. This is accomplished by using special coatings. More on that later. Of course, the right coat of paint isn't going to do anything to hide the sound made by a stealth jet. That's where acoustic stealth earns its stripes. This basically comes down to making the plane quieter. As a matter of physics, sound travels too slowly to serve as an effective targeting signal for anti-aircraft systems, especially at high altitudes. That means acoustic stealth is far more important for low-flying aircraft, and particularly reconnaissance planes, Then for high-speed stealth jets. Both the Chinese J-20 and the Russian Sukhoi Su-57 Felon, the two stealth jets currently most likely to be confronted by U.S. air defenses, have cruising speeds above Mach 2. They were designed to operate at high altitudes to enhance their stealth capabilities. You'll see these planes flying over before you hear them. Meanwhile, the U.S.'s F-117 stealth fighter, which is designed to fly at high speeds at very low altitudes, incorporates acoustic stealth measures including sound-absorbent linings inside its engine intake and exhaust cowlings. But in terms of detecting and taking down enemy stealth aircraft, there's a more sophisticated and reliable method available: infrared detection. Infrared radiation is emitted by all matter above absolute zero. Hot materials such as engine exhaust gases or wing surfaces heated by friction with the air emit more infrared radiation than cooler materials. Heat-seeking missiles and other weapons zero in on the infrared glow of hot aircraft parts, so the goal of infrared stealth is to keep aircraft parts and emissions as cool as possible, particularly those associated with engines. Embedding jet engines inside the fuselage or wings is a typical design component of infrared stealth. Other methods used to reduce an aircraft's heat signature include shielding hot components, mixing cooler air with engine exhaust before it's released, and splitting of the exhaust stream by passing it through parallel baffles. Special coatings are often applied to high-temperature areas to absorb and spread out the heat, making it harder for infrared sensors to lock on. These passive stealth countermeasures can be combined with active stealth measures like infrared jamming. This is where flickering infrared radiators are mounted near engine exhausts to confuse the tracking circuits of heat-seeking missiles. But as the technology and materials to increase infrared stealth develop, so too do infrared detection methods. Infrared Search and Track Systems, or IRST, have been in use by the U.S. military since the 1960s, and the sensitivity and quality of the instruments have steadily improved. In the 21st century, IRST systems have become an increasingly vital tool for detecting and eliminating short-range air threats. The U.S. military has recognized their value and has either integrated or is in the process of integrating systems like the Northrop Grumman Open Pod into its fighter fleet, including the F-15, F-16, and F-22. These systems act like powerful thermal cameras that can spot distant enemy targets and use the data to neutralize the threat. The F-35 is equipped with the AN/AAQ-37 Distributed Aperture System (IRST), which consists of 6 infrared sensors around the aircraft. This gives it full spherical coverage, providing day or night imaging and acting as an IRST and missile approach warning system. Military analysts believe the J-20 and Su-57 also have a similar design concept integrated into their systems. The beauty of IRST technology is that it is completely passive and does not light up the location of the aircraft, unlike when a pilot decides to use onboard radar, which can give away its position as radio frequency energy bursts out. IRST can also work in all weather conditions, as it uses the infrared rather than the visible part of the electromagnetic spectrum. That said, the worse the weather, the shorter the detection range becomes. Also, the higher the altitude, the less dense the atmosphere, and so the less infrared radiation it absorbs, especially at longer wavelengths. And at high altitudes, temperatures range from 22 to -58 degrees Fahrenheit, which provides better contrast between aircraft temperature and background temperature. That means IRSTs have longer ranges at higher altitudes, which is why they are primarily used on fighter aircraft. It also means that they're only really effective short range, which limits the fighter's scope to launch heat-seeking missiles against the targets they detect. The net result is that although IRST is a valuable component of the U.S. air defense shield, it's likely to become even more valuable as the technology becomes even more refined. But it's not the main method used to detect and eliminate stealth jets. For that, you need long-range detection, and for long-range detection you need radar. In essence, a radar antenna sends out a burst of radio energy, which is then reflected by any object it happens to encounter. The radar antenna measures the time it takes for the reflection to arrive, and then it uses that information to calculate how far away the object is. The metal body of an airplane is very good at reflecting radar signals, which makes it easy to find and track airplanes with radar equipment. For almost all non-military aircraft, being detectable by radar is a desirable trait. That's why almost all of them have circular shapes, which not only makes them more aerodynamic, but also makes them excellent radar reflectors. No matter where on the plane the radar signal hits, at least some of the signal will be reflected. However, when it comes to stealth aircraft, those radar reflections are exactly what you want to avoid. In fact, the primary goal with the current stealth technology is to reduce the radar cross-section, or RCS. In layman's terms, the aim is to make the aircraft as invisible to radar as possible, and for as long as possible. That essentially comes down to optimizing the jet to defeat higher frequency bands, particularly the C, X, Ku, and the top part of the S bands. This is accomplished by absorbing incident radar pulses, actively canceling them by emitting inverse waveforms, deflecting them away from receiving antennas, or all of the above. As noted earlier, metallic surfaces reflect radar, so to absorb radar pulses, stealth aircraft parts must either be coated with radar-absorbing materials or preferably made out of them. And that's because an aircraft built with intrinsically radar-absorbing materials gains both stealth and aerodynamic advantages. In contrast, applying radar-absorbent coatings offers no aerodynamic benefit. It's essentially just added weight. Many radar-absorbent plastics, carbon-based materials, ceramics, and blends of these materials have been developed for use on stealth aircraft. However, their effectiveness is magnified when combined with radar-absorbing surface geometry. That's why stealth aircraft typically sport a highly angled and streamlined design. Wing surfaces can be built on a metallic substrate that's shaped like a field of pyramids, with the spaces between the pyramids filled by radar-absorbent material. Radar waves striking the surface will zigzag inward between the pyramid walls, which increases absorption by lengthening the signal path through the absorbent material. Metal screens over the intake vents of jet engines, like those used on the F-117 stealth fighter, can also be used to absorb radar waves, exactly like the metal screens embedded in the doors of microwave ovens. Highly angled surfaces are also a key component in deflecting radar waves. Most radar systems are monostatic. That means most radar systems either use the same antenna for both sending and receiving signals, or a separate receiver placed very close to the transmitter. So for stealth work, radar pulses must be deflected in any direction other than straight back to the source. That's why stealth aircraft can't have flat vertical surfaces. They act like mirrors, bouncing radar directly back to the enemy. And that is exactly why the B-2 bomber is shaped like a boomerang. The combination of these two strategies, absorption and deflection, enables stealth jets to hide from high-frequency radar. But why do stealth aircraft need to be hidden from high-frequency bands in the first place? That's a matter of physics. There's a step change in a low observable aircraft's signature once the frequency wavelength exceeds a certain threshold and causes a resonant effect. Typically, that resonance occurs when a feature on an aircraft, such as a tail fin, is less than 8 times the size of a particular frequency wavelength. Effectively, smaller stealth aircraft like the J-20, without the size or weight capacity to carry those thick radar-absorbent coatings on every surface, are forced to make trade-offs. They must choose which radar frequency bands to optimize against, rather than achieving broad-spectrum stealth. That means a radar system operating at a lower frequency band, such as parts of the S or L band, like civilian air traffic control ATC radars, are almost certainly able to detect and track tactical fighter-sized stealth aircraft. However, a larger stealth aircraft, like the B-2 Spirit, which lacks many of the features that cause a resonance effect, is much more effective against low-frequency radars than a J-20 or Su-57. Typically, however, those lower-frequency radars do not provide what Pentagon officials call a weapons-quality track needed to guide a missile to a target. Going back to our example of the detection of the J-20 approaching Camp Humphreys, it would almost certainly have been detected by air traffic control at Incheon International Airport, South Korea's main commercial airport, but without the resolution necessary to launch against it. The US, along with Russia, China, and others, is developing advanced UHF and VHF band early warning radars that use even longer wavelengths. This will give their fighters a clearer idea of where an adversary's stealth aircraft might be coming from. But the basic problem remains. With long wavelengths come larger radar resolution cells, and the larger they are, the more difficult it becomes to achieve a clear enough signal to guide a weapon onto the target. More difficult, but not impossible. Traditionally, guiding weapons with low-frequency radars has been limited by 2 factors: the width of the radar beam and the width of the radar pulse. However, both limitations can be overcome with signal processing. Phased array radars, particularly active electronically scanned arrays, or AESA for short, solve the problem of directional or azimuth resolution by steering the radar beams electronically. AESA radars can also generate multiple beams and shape those beams for the desired width, sweep rate, and other characteristics. And that brings us to the primary way the US detects and targets enemy stealth aircraft: a combination of high-speed data links and low-frequency phased array radars. This is currently the most effective way to both identify the presence of stealth aircraft and generate a weapons-quality track, and it is precisely the way the J-20 from our opening scenario was shot down. Here's how the US did it. Central to the show is the Northrop Grumman E-2D Advanced Hawkeyes Airborne Early Warning Aircraft, or more precisely the Lockheed Martin AN/APY-9 UHF band radar, which is its main feature. The AN/APY-9 operates in the UHF band and is known for its high reliability and solid-state transmitter design. This provides maximum waveform flexibility and increased sensitivity. The radar's electronic sector scanning capability allows for faster track updates within any 90-degree arc, significantly boosting its ability to detect smaller targets at longer ranges. This is especially effective in complex environments like coastal regions and over land, where clutter and terrain can typically interfere with detection. Rotating at 6 revolutions per minute with a detection range of 350 nautical miles, it detects and identifies the J-20 in short order. The APY-9 then cues Raytheon AIM-120 AMRAAM air-to-air missiles on board FA-18E Super Hornet fighters linked via the Link 16 data link. Link 16 is a standardized communication system used by US, NATO, and coalition forces. It transmits and exchanges real-time tactical data using links between allied military network participants. It's a secure, jam-resistant, high-speed digital data link that operates in the radio frequency band of 960 to 1215 MHz. Link 16 enables military aircraft, ships, and ground forces to exchange their tactical picture in near real time, supporting the exchange of text messages, imagery, voice, and more. With target cues received via Link 16, the Super Hornets launched the AIM-120s. The result is a J-20 ending up as a stealthy hunk of twisted metal on the bottom of the South China Sea. The AP-9 radar can also serve as a remote sensor for guiding Raytheon's standard SM-6 missiles launched from Aegis cruisers and destroyers. Using the Cooperative Engagement Capability, or CEC data link, it can relay targeting data on threats located beyond the horizon of the ship's onboard Spy-1 radars. CEC is a sensor network with integrated fire control that merges data from multiple air search sensors into a unified real-time composite track picture. This shared network allows for different platforms, such as ships, aircraft, and other CEC-equipped units, to seamlessly exchange targeting data. The result is a dramatically enhanced fleet air defense system that not only makes electronic jamming more difficult, but also enables coordinated missile defense across an entire battle group. For example, it integrates with F-35C Lightning IIs, which act as forward observers, relaying target data through the E-2D Advanced Hawkeye to less stealthy platforms like the Super Hornet. So that's how the US is able to take out enemy stealth jets, for now. But what new stealth threats might the future hold? The US's main rivals have several new stealth aircraft in various stages of development. At least 3 prototypes of China's next-generation stealth fighter, the Shenyang J-31, are known to have been built. Also known as the FC-31 Gyrfalcon, this medium-sized stealth multi-role fighter features a twin-engine layout powered by 2 RD-93 afterburning turbofan engines, each producing 84 kilonewtons of thrust. Designed to rival 5th-generation Western jets, it boasts a suite of advanced features, including an IRST sensor, redesigned stealthier wings, cleaner burning engines, and an upgraded radar system. Together, these enhancements could present new counter-stealth challenges for enemies. Even more problematic to detect and take out, if they can ever get it off the ground, will be China's next-generation stealth bomber, the Shan H-20. It's designed with a flying wing configuration reminiscent of the B-21 Spirit to minimize its RCS, radar-absorbent materials, and advanced electronic warfare capabilities, and it's expected to have a range of over 6,200 miles. Russia also has 2 new stealth aircraft deep in development. The Tupolev PAK-DA, also known as Poslanik, which translates to Envoy, is a proposed Russian strategic bomber designed as a flying wing aircraft similar to the B-2 Spirit. It incorporates advanced avionics, internal weapons bays, and artificial intelligence to assist with navigation, mission planning, and threat detection. It's expected to have an operational range of approximately 7,500 miles, allowing it to conduct long-range missions without the need for mid-air refueling. Russia also has a new stealth fighter supposedly almost ready for production, the Sukhoi Su-75 Checkmate. This is a single-engine 5th-generation stealth fighter designed to be a cost-effective alternative to Western counterparts like the F-35 Lightning II. The Su-75 features a sleek, streamlined design with a blend of curved and angular lines a highly advanced avionics system including advanced radar, electronic warfare systems, and communication systems. It also has an internal weapons bay, AI integration, multifunctional radar, and network-centric warfare capabilities. And then there's the prospect of the 6th Generation Stealth Aircraft, or SGSA, which promises to be much harder to detect, let alone shoot down. Of course, since the US's enemies are still playing catch-up when it comes to stealth, 6th Generation counter-stealth measures are likely to be an even bigger headache for them than for the US. With the US developing new ways to detect them, are we entering the end of the stealth era? Let us know what you think in the comments below. Now go check out enemies who are terrified of the new F-22 replacement. Now we know why. Or click on this video instead.